So I'm going to start. So this is a talk about test-driven development and robotics. So has anyone run into test-driven development before? Do they know what that means? Go for it.
Basically, you build your robot layers of tests that you make sure that all work. That way you're really free.
Yes. So the goal is to write a lot of tests. And as you're building your robot, you have test cases to show that all the little pieces work. And one of the really cool benefits of this is you can start programming before the hardware exists. So I don't know about your teams, but on 971, we get the hardware in the software team right about week 6, the day before ship. And it takes us 2 to 3 weeks to program it. So we cannot start when we get the hardware. We have to start beforehand. And on our robots, we can't afford to crash them. So if you slam an arm into a limit, we will break them, cause weeks of damage. So we're very incentivized to get it right from the beginning. And that means a lot of testing and simulation. So I'd like to walk you guys through we'll start with a simple example. So we have this elevator here from Citrus Circuits, who's kindly lent us their robot. And I have a little simulation model I've got for the elevator, which I believe should be pretty accurate. And we'll go write some tests against that and control it and zero it. And then after we've got our code written and we believe it works, and we've debugged it, all the simulation, then we're going to deploy it to the real hardware and see if we got it right. So, yeah. So let's start out. So I've got, in order to make this work, we have our elevator class here, elevator loop. So this is the class that's going to control our elevator. So it's pretty simple. It has 2 methods here, a bunch of constants. There's a set goal method, which you tell it what height to send the elevator to in meters. And then there's an update method. As the comment says, update needs to be called at 100 hertz, returns the voltage to apply to the motor. And it takes the current position, if the limit sensor is triggered, and if it's enabled. So our first step is we need to go write a little simulation that will let us call update. Try and simulate our system. People following along? I'm going to hopefully have you guys help, because I don't want to be right. I can write this code pretty quickly, but I'd like you guys to interact with it. So we have a function here, which I've worked out the physics for already. Get acceleration. So this function returns the acceleration of our robot given a voltage. Okay. So how many has anyone taken basic calculus? Actually, that's a surprisingly large amount. Let's backfill a little bit. So we don't have to get this perfect. We don't have to actually solve the calculus here. We can cheat aggressively because we can use computers. Okay. So the basic idea is, does anyone know how to get from an acceleration to a velocity? Assuming the acceleration is constant.
You take the integral of this.
Okay. But let's try and break this down. So we have time. Okay. Say our acceleration is a constant. We want to figure out given a v0 at the start, what's our v0 here? A delta t.
Acceleration times time.
Yes. Plus the start. Okay. So that works if this is constant. So what if our acceleration is instead have some function here? So what we can do is we can go draw a bunch of little boxes, just split it up in a bunch of little chunks. And over the area between these, the interval will be the area under this. As you can see, the area is these little triangles. And if we make our boxes really small, it'll be small enough that we can ignore it. So that's going to be our way we're going to get from acceleration to velocity. So let's start it. Okay, I'm going to have to simulate jump motion. So how would we do that? Throw something at me.
First, you should split up the amount of time you're simulating for into small intervals. So probably like a quarter loop, or decide what each time step's going to be in the loop over like time divided by time step.
Or the 10th of a millisecond. place to say velocity. Like that? Kind of what you were thinking?
Yeah.
Time starts out, say someone asks for 0.1 seconds.
Oh.
We, while we still have time left, we remove some over and over and over. Okay, so now we need to get a position out because this elevator moves to positions. How do we do that?
The same thing, but instead of multiplying acceleration by times, I multiply velocity by times.
Okay. Great. So now we want to step out a layer. So now we can simulate a 10 millisecond control loop cycle. So now we want to simulate what happens when we execute our control loop, and then simulate, and then time elapses, and then we execute it. Time elapses again. Trying to simulate what would happen in our real robot. People following where we're going?
Mostly.
Mostly. What's not making sense?
Oh,
Okay. Yeah.
Wait, can you elaborate on what you just said on how we're using the actual?
So what we're going to do next, sure.
Yeah.
So let's try and think about how our robot's going to execute our software. So we have our function up here that we've defined, update. Update takes our sensor values and returns a voltage. And we're going to execute this at 100 hertz. So 100 times a second, we're going to call update. It's going to take the current sensor values, it's going to return something to do, and we're going to give that to our motor controllers. They're going to go do it for 10 milliseconds, and then we're going to repeat that process. So we want to go write a little simulation. Now that we can go simulate time here, we want to write a simulation that takes that into account now. Let's our control loop update. So how would we do that?
I'm not too sure.
Okay. So here we'll loop 100 times. So what would the steps be? Kind of how would we break our hardware down? Break it down to a simulator. Have a loop object. So the pieces are we have loop.
Did you just use a simulate time function this time?
I do, Katie. Do you see what we're doing here? Awesome. Okay, except our update function, which I didn't fully fill in, takes an encoder, a limit sensor triggered, and an enable bit. We gotta go make those signals up.
So just take the position that the robot's at from the simulation and make that the position for the reads.
Is that fully accurate?
Well, the encoder reads and
We've already converted. I've got that taken care of. Is that fully accurate with an encoder? Where's 0 on an encoder?
well, it's relative to it.
Wherever you turn it on.
Oh, I just assumed you would say that.
No, we got to write that code, which is what we're going to have to write our update function so it does a 0 procedure. So it's going to be wherever we turn it on. So, you guys following that? I see at least one nod. Okay, because that one's key. When we turn our robot on, the encoder starts at 0. And right now, 0 could be at the bottom. 0 could also be halfway up if you turn it on there. So that's not. So we need to simulate that correctly and make sure we handle that. So let's write it this way. We're going to start at 0 for now, and then we can test that later. We should go write a test case for that. Make sure it handles it correctly.
So you just pass your starting position. That can be set right now.
So then our encoder should read our position minus our starting position. Get that right? Okay. What else did we need? We need to simulate a limit sensor. So it took us a little while to find it on this robot. This is the first time I've used this one. So there's a magnet right here. Or no, sorry, there's a Hall effect sensor right here and a magnet on the carriage. So to zero this, we're going to drive the elevator up until the magnet, until the magnet goes by this limit switch. So we got to come up with a function that's going to simulate this limit switch for us. Somebody have any ideas on how we write that?
If we read the position, so that's our type, and that trigger stream for that big.
Okay, and what if you keep going?
So we have the position keeps, or it turns off.
Yes. So there's a little range. Yep, sorry.
So we want to see if it's within some, if they're, close, within some range.
Yes, we want to make sure it's close to, the center where the magnet and the sensor is. If it's close to that, it's going to be on, otherwise it's off. So we can write a little function to simulate. So for grins, I'm going to define 0 to be when the limit sensor is triggered. We're going to just make it easy that way. Actually, let's stay at the bottom of the limit sensor. I figure out how tall it is. About half an inch tall. It's about a centimeter. Okay. Okay, and we're always in it. Okay. Compiling, see how close we get. Hold on. Where did Jennifer go? Okay, so free speed's missing. Okay, I think we need to start writing a little bit of an implementation. We have nothing to run against. Let's try the simplest possible thing, just to see how well we're doing. So our elevator is going to do nothing. Just to see if we can get it to compile. Got some more. Test pass. Okay, so what's that mean here?
We didn't assert anything.
Yeah, we didn't do anything useful. So we should probably go start testing for something. One of the tenets of test-driven development is you try and this is a little pure, not everybody does this when they do it for real, but you're supposed to write your test. Your test is supposed to fail because your software doesn't implement it yet. And then you go write your software to make it pass. So we should go write a test now that goes and fails because we failed to do something. So I'm going to make this run a little longer. So what if we tried to go somewhere? Try to go to point 1, and then we can go okay, how close should we be? Half a centimeter? I have a proposal for half a centimeter. That's saying reasonable. So we're going to say our test passes if we get within a half a centimeter of our destination. Okay.
Are you saying
So we use SI units here. Everything is radians, volts, meters, kilograms, seconds. Did I miss any? Newtons, amps. They just end up working better. So on 971, if we need to get to and from feet, we convert right at the beginning, run all our math and metric, and then convert at the end back to the user. You avoid a lot of conversion problems. So yes, it's all in meters. Okay, I think I got to write a goal getter. Okay. Test failed. That's progress. It's good because our code doesn't do anything yet. Let's read this. So the difference between position, which is where it actually is, and loop.goal is 0.1, which exceeds our half a centimeter. So we didn't move. Cool. So we should probably go make it move now. Okay. So let's describe the process that I think we should use for zeroing, and then we'll go implement it. Does everyone know what zeroing means in this context? Yeah. I'm seeing nods from everywhere. That's good. So we want to do this under control. I turned this thing on to test it a little bit earlier to make sure I got positive and negative right, and it goes really fast, which is it's expected. So we want to, in a very controlled fashion, move up slowly, and then move until we see the sensor, and then capture that value, and then we can go quickly. Because that lets us make sure that if the user asks us to go up through the ceiling, we don't go through the ceiling, and we don't break the robot. So, I like the software design pattern I like to use for this is I like to chain things together. So we'll have a little control loop, a little PID loop. Okay, so this is going to take in a goal. It's going to output a voltage. And then we'll write a little piece of software that to implement zeroing changes the goal to move the robot. So we have one piece of software that's designed to move it in a controlled fashion. And then we have another piece of software that either does what the user's asking for, or it moves it slowly to zero. Okay, this is, I like it. It'll be a little state machine. Let's take an easy request. Does that make sense to people? Okay. Well, always have state machines. We should probably draw out our states. What are some states people think we should use?
Not zero.
Not zero, good.
Zero.
Zero, great. Rather than zero, I like to use running. It's really the same thing. Just like our system is operating normally. Okay. Disabled, yep. All right, so we'll go from disabled, start drawing arrows. So when do we move from disabled to not zero? Okay, great.